we're going to walk through some simple linear regression and then also some multiple linear regression. So to start, we're going to begin with an example that uses a Ames housing data set to perform some exploratory data analysis, and then we'll create a correlation matrix and then build and test a simple linear model. So first we're going to need some libraries. We're going to use sklearn to pull some data, so we're not uploading a file, we're using publicly available data, and then also to pull our linear model package and some metrics that we can use to assess our model. And then of course we'll also be using pandas, numpy, and matplot library, and then seaborn for some visualizations. Okay, so let's go ahead and load the data set. We're using the Ames housing data set, which again we can pull from sklearn. I am no longer using the Boston housing data set from sklearn. It had some ethical issues with that data set, so we're going to use this other one instead, which also works well for practicing on regression. The first thing we're going to do is grab the data and place it into a data frame. So we can do that using this fetch OpenL command. And we're going to place it in this data frame called data. And let's see what it looks like. So we'll start with printing the first 5 rows of the data set. We can see we've got 5 rows and 81 columns. So they're not all shown here, but this is a good indicator of kind of what the data is. It looks like some of these variables have a lot of nulls or not applicables. I do see some good potential numerical integer values for regression. Let's print the descriptive statistics for each of our numeric variables. And when we do this, now we can kind of see, all right, so we've got some good variables here to work with. Looks like overall condition, year built, year sold, wonderful, sale price. Okay. Finally, let's print some information on the columns and their data types. So when we do that, we get all the columns listed here, all 80 of them, and then which ones are integers, objects. We can see how many values are non-null in there. So there's 1460 entries, so just over 1,400 entries, and for the 81 columns, it looks like, for example, lot frontage has about 259 nulls. Alley has a lot of nulls and very few. So this kind of tells us which variables we might want to stay away from, or we might want to drop altogether. We're not going to drop any in this tutorial, but we're not going to get much value out of a variable like this, where there's only 7 values that are non-null. Okay, moving on. Let's look at a correlation matrix. This correlation matrix is going to be really large, so I've done a couple of things. First I have to pre-process the data because I can only generate a correlation matrix with numeric columns. So I created this sub data frame, and I'm going to select the D types that include number. Then I'm going to generate just a diagonal correlation matrix. I don't need the upper and lower diagonals because they tell you the same thing. So to do that, I'm going to build my correlation matrix just like we did before, and then I'm going to actually use this mask here to drop the numbers, because when they print on a really large correlation matrix, they get all scrunched together, so they're not very useful. And then I'm going to plug those into the SNS heat map. So it takes this argument correlation matrix, which takes the correlation data. It takes this argument mask, which is going to tell it not to print those values. I'm going to set the color map to cool warm, the argument square to true. I'm going to set my line widths here. And then I'm going to give it a title, and I'm going to click show. Here it is. It's quite large, but we can kind of see at a glance which variables, like for example, this one. So total rooms above ground and ground, I don't know if that's grade or ground living area, but either way, those are highly correlated. Let's look at sale price and see what might be good predictors of sale price. So here's sale price here. Overall quality. This living area one here, and then some that are moderately correlated as well. So we can kind of see that there's potential here for a good linear model that predicts sale price. So let's go ahead and start doing that. So to do that, we do need to split our data up into a training set and a validation set. Our target variable is going to be sale price, so we're going to set that here. And then for our predictor variable, it looks like this is the best one. I'm not going to use overall quality because technically that's a categorical scale from 1 to 10 and not true like a true integer variable where it's continuous. So we're going to go with the first highest correlated continuous variable. And set that. Then we're going to split our data set 80-20. So I set aside test size 20%. And now we're going to build our model. So let's go ahead and run this to split our data. Okay, so we want our model to be a linear regressor, and that means we have to call this linear regression function. And then we're going to put in there X train and Y train. Okay, looks like it ran just fine. Let's look at the coefficient and the intercept. Perfect. That doesn't tell us a lot though on its own. So let's see what a scatter plot of our data looks like. Okay, so in our scatter plot we've got our training data, and we also can plot our linear regression line, and I made it red, and then titles and axes labels. So it looks like as the living area square feet gets really large, our sale price gets quite variable. So this may not be a very strong regression, but we can evaluate it by looking at the mean squared error and the R squared value. So here's the code to do that. We're gonna use the this code here to run the predictions using the X test set of data. And then from there, we can calculate mean squared error. So we're comparing the test to the predicted, and then the R squared, comparing the test to the predicted. And when we print those out, okay, so our R squared, our mean squared error is pretty high. Our R squared is only 0.55. So ideally we'd like to see something higher. This is telling us our model with that above grade living area square feet only explains about 55% of the variance in sale price. Let's see if we can create a different model and see if maybe we can get a better model. So we're going to switch gears here for a second. And I want to see if we saw that overall quality, even though it's categorical, we saw that it was highly correlated to sale price. So I want to explore that more. And in order to do that, since it's categorical, a box plot is the best way to assess differences in the sale price between each of those ratings 1 through 10. So to do that, we can use this box plot feature, and we just tell it that we want overall quality along the x-axis, and then we're assessing sale price. And so when we do that, we can see very clearly that in fact it does look like there are significant differences between sale price for each of these quality ratings. So that's kind of interesting. let's set our predictor and target variable for overall quality now and sale price and see what happens if we run this model. So we're going to go ahead and build this model same way we did before. We got a new coefficient and intercept, and then here is the training set predicted, the training data versus the regression line. So that's kind of interesting. And then we'll go ahead and evaluate the model. And what I mean by when I tell you that this is technically categorical, you can see that now when you look at the scatter plot, because they're all lined up along the categories for the rating. So that's kind of how, if you ever do a scatter plot and you see this, then you know that your variable along the x-axis is actually categorical. But we did get an R squared of 0.65, so that model performed better. That's not bad for simple regression. And if we did predicted versus actual, we can see again that our at these higher house values, everything kind of, the error gets much larger. Okay, so that's it for simple linear regression. Now let's move into multiple regression. We want to generate a better model. Generally, if we want to do that, we're going to need more than one predictor variable. So that would be multiple regression. And we're going to try and improve upon that first model, the model that we've been playing with here where we're predicting sale price. So we're going to pull in overall quality. We're going to pull in the living area. So those are the two that we did alone. We're also going to pull in this garage cars and total basement square feet. Okay, so now to do this, all we're doing is we have more than one predictor, so we're just going to put our predictors into a set here, and then our X will be the data that will pull the predictors, the columns for the predictors, and our Y will be the sale price column. Now we're going to split the data into training and validation again. So same process here. This is all going to look very familiar. We're still going to, same linear model code. It's just using multiple predictors now. And then if we print our coefficients, we get a coefficient for each of them and the intercept. And if we evaluate the model, we can see that we got all the way up to almost 0.8. So this is not a bad model at all. What does it look like if we plot the predicted versus actual? Pretty good until you get up to these higher values. Now, we should do a little more investigation on our regression models before we accept them. So we're going to check to make sure that all of the coefficients are statistically significant. So they have p-values less than 0.05. And we're going to need stats models to do that. So we'll have to import some new libraries. And then we're going to add a constant to the model. It's just something we have to do for stats models. So we're adding the constant to this the X data set. And then we're going to split the data again. For the model, if we use stats models, it's just a slightly different command to run the regression model. And then that allows us to print the model summary, and we get this really nice ANOVA printout that might look a lot like when you run ANOVA in Excel. And we can see for this, the regression, the R squared was a little different, but similar to what we ran before. It looks like all of our variables are statistically significant, so that's great. And then the nice thing about running ANOVA is that you have other statistics that you can use to assess the quality of your model, like whether there's any skew, kurtosis, and stuff like that. For the purposes of this class, though, we're just checking to make sure that all of our variables are significant. The last thing we want to do is make sure that our model doesn't have multicollinearity. So we don't want two of our predictor variables to be highly correlated to each other, because that can lead to overfitting with our model. So to do this, we're going to check the variance inflation factor. The variance inflation factor measures how much the variance of a regression coefficient is inflated due to multicollinearity with other predictors in the model. So if it's equal to 1, there's no correlation between the predictor and any other variables. If it's between 1 and 5, it's moderate correlation, which is acceptable. If it's greater than 5, now we're getting problematic. And if it's greater than 10, then it's severe and it's dramatically affecting the results of the regression. So when we calculate, to do that, we'll just pull the predictor variable data, so that's X, pull the columns, and run this for each predictor variable. We're going to calculate the variance inflation factor, and then we're going to print that data. So we basically just created a blank data frame, and then set up a variable column, and then a column to calculate the variance inflation factor. And then, so when we do that, see, here's our variable column here, and here's our variance inflation factor. So when we print it, we get more like a nice table. So we can see that all of our variance inflation factors, we don't really care about the constant. We're just looking at these 4 here. They're all less than 5. So we're good. We feel good about our model, and we're happy with the R squared. So this is a pretty good model overall.